Hello. Alright, so this time we want to calculate the enthalpy change using the Born-Haber cycle. So the Born-Haber cycle, it is an energy level diagram which is similar to the Hess diagram. But this Born-Haber cycle, it is an energy level diagram. So tofanirwa kuziva kuti patichange tichidrowa isusu the Born-Haber cycle tine ma-arrows, one riri kuenda up, the other one riri kuenda down. Ma-arrows either ari kuenda up kana kuti ari kuenda downwards. So an exothermic enthalpy change must be shown using a vertical arrow pointing downwards. So if the arrow is pointing downwards like this, it means the reaction is exothermic. Then for an endothermic reaction, the arrow is also vertical but pointing upwards. So this one is for endothermic. This arrow going downwards is for exothermic. Alright, so this Born-Haber cycle is for an ionic compound. So chakakosha pakunge uchiita nezve this Born-Haber cycle, tikufanira kunge tichigona kuziva anonzi ma-definitions first. So the first definition yatiri kuita nezvayo inonziyo electron affinity. So in general, electron affinity is the enthalpy change when one more of electrons is added to one more of gaseous particles. So we have first electron affinity. So first electron affinity, we are adding one more of electrons to one more of gaseous atoms. So this change is exothermic. So for example, we've got this oxygen atom here, it is neutral. So the nucleus is positively charged, so we're adding an electron. We need to add an electron. So we have formed a negatively charged. So by adding one electron to each mole of gaseous atoms, we are forming an ion. So this ion is negatively charged. So we're going to have this ion with a negative charge. So because this electron is negative and the nucleus is positive, so there is an electrostatic force of attraction between these two species. So energy is released. That's why the change is exothermic. But what happens when you add the second electron? Now, by adding the second electron now, because we were adding an electron to a species which was already with a negative charge, so remember the rule, like charges repel. So a lot of energy is needed to overcome repulsion. So since we have formed the ion with a charge of 2 minus, so we are adding electron to an anion. So energy must be supplied to overcome repulsion. So that was the second electron affinity. So second and afterwards electron affinity are always endothermic. This is because of the repulsion between the incoming electrons and the negative ions. So that's why the second value is plus 844 for the second electron affinity. Another definition is standard enthalpy change of atomization. So it is the energy absorbed, so the reaction is endothermic to form one more of atoms in gaseous state from the element in its defined physical state under standard conditions. For example, in this case, magnesium is a solid at 25 degrees Celsius and 1 atmosphere. So we are converting magnesium in solid to magnesium atoms, one more of magnesium atoms in gaseous state. So energy supplied, so we need 148 kilojoules per mole. So for example, let's say we have another for example, let's say we've got sulfur exists as S8 and it is a solid. By definition, we are going to form one more of sulfur atoms in gaseous state. So how many moles of sulfur do we need? We need 1/8, 1/8 mole. All right, so the difference, sometimes we use bond energy. So bond energy, so sometimes we say mean bond energy. So mean means average. So it will be the average energy required or average energy absorbed when one more of XY bonds are broken in gaseous state. So when determining bond energy, we are starting with one more of the substance in gaseous state. So for example, let's say I've got oxygen here. Oxygen exists as a molecule. It is like, in this case, we can use the bond energy to calculate enthalpy change of atomization. So oxygen, so this is oxygen. So oxygen has got a double bond. So we need to break the double bond. So to break the double bond, we are going to form 2 moles of atoms. So we started with O2 in gaseous state, then we formed 2 oxygen atoms in gaseous state. So to form 2 moles, we need 496. So what about, by definition, atomization, we form 1 mole. So to form 1 mole, we divide by 2. Then the energy, so enthalpy change of atomization of oxygen will be equal to 200 positive, so it's plus 248 kilojoules per mole. All right. Then another definition is first ionization energy. First ionization energy is the energy absorbed to remove 1 mole of electrons from 1 mole of gaseous atoms to form 1 mole of gaseous unipositive ions. So like in this case, magnesium, we are starting with magnesium in gaseous state. we are going to form magnesium ion in gaseous state plus one more of electrons. In this case, we are supposed to absorb or supply 738 kilojoules per mole. Then the second ionization energy, it is the energy required to remove one mole of electrons from one mole of gaseous unipositive ions. So we are starting with Mg plus. So we are going to form Mg2 plus in gaseous state. As usual, we are losing one more of electrons. So we have to overcome the electrostatic force of attraction between the positively charged nucleus and the valence electrons. Hence, energy must be supplied. All right. Then another definition is lattice energy. It is the energy change when one mole of an ionic crystal is formed from its isolated gaseous ions. So this one is exothermic. It is always exothermic because it only involves bond formation. Okay, so factors which affect lattice energy. So lattice energy is directly proportional to the product of charges divided by the sum of ionic radius. So the bigger the charge, so for example, if you say Q plus, which is the cationic charge, Q minus is the anionic charge, then R plus is the cationic radius and R minus is the anionic radius. So Q plus divided by R plus, that's the charge density of the cation, and Q minus divided by R minus is equal to the anionic charge density. So the larger the charge density, the stronger the electrostatic force of attraction, and the more exothermic the lattice energy. And lattice energy is an indicator of ionic bond strength. So the higher the lattice energy, the higher the melting point and the stronger the ionic bond. So for example, in this case, sodium ion with a positive, so sodium ion Na plus is bigger than Mg2 plus, but Mg2 plus has got, that magnesium ion has got a bigger charge and a smaller cationic radius. So in other words, we say magnesium ion is higher charge density. Then comparing anions, chloride ion is bigger than oxide ion. So but oxide ion again has got a bigger charge, so oxide ion has bigger charge density. Hence we have stronger ionic bond between magnesium ion and oxide ion compared to the sodium ion and chloride. So for example, like in this case, the lattice energy of sodium chloride is minus 786 kilojoules compared to the minus 3790 of magnesium oxide. In this, we are supposed to answer this question. Draw the Born-Haber cycle for magnesium oxide and use it to calculate its standard enthalpy change of formation. All right. So the first thing chatiri kufanira kunge tichiisa tinodraw line redu pekupedzisira pasi panapa. Unofanira kudraw riri horizontal, then we put magnesium oxide in solid state. Zvakakosha kunyora ma-state symbols. Then to draw arrow. So the first change yatinayo is enthalpy change of formation. Ndo yatiri kutsvaga iyoyo. Then takuisa ma-elements edu. We have magnesium, ma-state symbols akakosha in solid state, plus oxygen. We need half more of oxygen in gaseous state. Then next we are going to have enthalpy change of atomization of magnesium. Then we are going to have Mg in gaseous state plus half oxygen, half more of oxygen in gaseous state. Next step is enthalpy change of first ionization energy of magnesium. Magnesium in gaseous state plus we are losing one more of electrons plus half more of oxygen. Then next it's enthalpy change of second ionization energy of magnesium. So we are losing electron from magnesium ion. So we are going to say Mg 2 plus in gaseous state plus 2 electrons plus half more of oxygen in gaseous state. Then the next thing is enthalpy change of atomization of oxygen. All right, now so we now have oxygen atom. So the next thing is enthalpy change of first ionization energy. So it is exothermic. So we are going to have magnesium ion. So we lost one electron. So plus an electron plus or minus in gaseous state. Next, so in terms of magnitude, second ionization energy of oxygen is bigger than first. Now we have Mg2 plus ion in gaseous plus oxide ion in gaseous state. Then we now going downwards, and this change from ions in gaseous state to an ionic crystal, this is the enthalpy change of lattice energy. All right, now we need to use the Hess law. So Born-Haber cycle rinongoshanda sezvinongoita Hess diagram. Value yatiri kutsvaga ndeino. Saka zvatakuchiita, toda kubva apa point iyi tinokwanisa kugadzira toda kubva apa tichiuya kupi, tokona kuti kubva apa tichiuya apa, kubva apa tichiuya apa, zvakafanana nekuenda kupi, nekubva apa tichitenderera neku totenderera nekuno, zvakafanana. Saka zvafanana nekuti kudini apa, saka takuchiti this value iri equal to yepanapa plus yepanapa zvichingoenda kwese kuti chingoramba chichieda because zvimwe zvese izvo zviri kuenda same root. Saka ndotatakuda kuchieda. Saka value yepanapa tamboiziva is plus 248. Yepanapa tamboshanda nayo. Alright, E taiziva it's minus 3790. Then E that is plus 844. E that is minus 141. Then atomization of oxygen. Cinema values among asara anwa iwo. Okay, atomization of magnesium. Atomization of magnesium is plus 148. Is plus 148. So plus 148. Then this one plus 738 plus 738. This one is plus 1451. 1451. So enthalpy change. So we are saying enthalpy change of formation is equal to 148 plus 738 plus 1451 plus 248 minus 141 plus 844 minus 3790. Okay, 148 38 plus 1451 plus 248 minus 141 plus 844 minus 3790. So the value, so the standard enthalpy change of formation becomes minus 502 kilojoules per mole. Alright, kuti tizive zvakawanda ngatisanganei pa next chapter kana kubatana pama social media platforms edu. ndatenda.